Welcome! In this video, we're going to solve LeetCode problem 1536, minimum swaps to arrange a binary grid. Let's start by understanding what the problem is asking. You are given an n by n binary grid. Each cell contains either a 0 or a 1. You are allowed to swap any two adjacent rows. Your goal is to find the minimum number of swaps needed to make the grid valid. Now, what does valid mean here? For each row I, where I starts at 0, all the cells after a certain position must be 0. Specifically, row I must have at least n minus 1 minus I trailing zeros. So for the first row, you need n minus 1 trailing zeros. For the second row, you need n minus 2 trailing zeros. And so on. The last row can have 0 trailing zeros. Think of it as a staircase pattern. Each row needs a certain number of zeros at the end. Now, let's look at the constraints. The grid is always square, n rows and n columns. The value of n can go from 1 up to 200. Each cell is either 0 or 1. And if it is impossible to make the grid valid, we return -1. Let's walk through some examples to make this concrete. Let's walk through example 1. The input is a 3 by 3 grid. Row 0 is 0, 1, 1. Row 1 is 1, 1, 0. Row 2 is 1, 0, 0. First, let's count the trailing zeros for each row. Row 0 has 0 trailing zeros. Row 1 has 1 trailing zero. Row 2 has 2 trailing zeros. We need to rearrange the rows so the grid becomes valid. Remember the rule. Row 0 needs at least 2 trailing zeros. Row 1 needs at least 1 trailing zero. Row 2 needs at least 0 trailing zeros. The valid output is row 0 equals 1, 0, 0, that has 2 trailing zeros. Row 1 equals 1, 1, 0, that has 1 trailing zero. Row 2 equals 0, 1, 1, that has 0 trailing zeros. All conditions are satisfied. So how do we get there? The greedy approach bubbles the nearest qualifying row up to each position. Swap 1. Swap row 1 and row 2, giving us 0, 1, 1 then 1, 0, 0 then 1, 1, 0. Swap 2. Swap row 0 and row 1, giving us 1, 0, 0 then 0, 1, 1 then 1, 1, 0. Now position 0 is satisfied. Swap 3. Swap row 1 and row 2, giving us 1, 0, 0 then 1, 1, 0 then 0, 1, 1. Now position 1 is satisfied too. The minimum number of swaps needed is 3. So the output is 3. Let's look at another example. Now, let's look at example 2, the impossible case. The input is again a 3 by 3 grid. Row 0 is 1, 1, 1. Row 1 is 1, 1, 1. Row 2 is 0, 1, 1. Look at the trailing zeros for each row. Not a single row ends with a 0. Row 0 and row 1 both need trailing zeros, but none of the rows in the grid have any trailing zeros. This is the key insight. Swapping rows only moves rows around. It does not change what is inside a row. So no matter how many swaps we do, we can never give row 0 the 2 trailing zeros it needs. It is impossible to make this grid valid. So the output is -1. Now that we understand the problem well, let's think about how to solve it. Now, let's think about the brute force approach. The core idea is simple. Try every possible arrangement of rows and find the one that is valid using the fewest adjacent swaps. Here is how we break it down step by step. Step 1. For each row, count how many trailing zeros it has. This tells us whether a row is good enough for a given position. Step 2. Generate all possible permutations of the rows. For an n by n grid, that is n factorial permutations. Step 3. For each permutation, check if it forms a valid grid. Remember, row I must have at least n minus 1 minus I trailing zeros. Step 4. For each valid permutation, count how many adjacent swaps are needed to reach it from the original order. This is essentially a bubble sort inversion count. Step 5. Return the minimum swap count found across all valid permutations. If no valid permutation exists, return -1. Now this works, but it is extremely slow. For n equal to 200, n factorial is astronomically large. We cannot enumerate all permutations. And for each permutation, counting adjacent swaps adds even more cost. This is why we need a smarter approach. Let's look at the brute force code first, then move to the optimal solution. Let's look at the brute force code in Python. At the top, we import permutations from the itertools library. This gives us a built-in way to generate all row arrangements. Inside the function, we first get n the size of the grid. Then we compute trailing zeros for each row. We loop over each row and scan from right to left. As long as we see a 0, we increment our count. The moment we hit a 1, we stop. We store the trailing 0 count for each row in the zeros list. Next, we try every permutation of row indices from 0 to n-1. We initialize best to infinity. This will track the minimum swaps found. For each permutation, we check if it forms a valid grid. We use the all function to verify that the row placed at position I has at least n-1-i trailing zeros. If the permutation is valid, we count the adjacent swaps needed to reach it. We simulate a bubble sort, repeatedly find the row that belongs at position I, and swap it forward one step at a time. Finally, we return best if a valid arrangement was found. Otherwise, we return -1. This works correctly, but generating n factorial permutations makes it far too slow for large grids. Let's now look at the time and space complexity to confirm. Let's analyze the complexity of the brute force solution. Starting with time complexity, the dominant cost is n factorial, the number of permutations we generate. For each permutation, we spend big O of n time to check if it is valid. Then, for each valid permutation, we spend big O of n squared to count the adjacent swaps using bubble sort. So the overall time complexity is big O of n factorial times n squared. To give you a sense of how bad this is, for n equal to just 8, that's already over 2.5 million operations. For n equal to 200, this is completely unworkable. Now for space complexity. We store a zeros array of size n for trailing 0 counts. The current permutation tuple is also size n. And we make a temporary copy of size n for the swap counting. So space is big O of n, that part is fine. The verdict is clear. The time complexity of big O of n factorial times n squared is completely impractical for large grids. We need a fundamentally better approach. Coming up next, let's look at the optimal greedy solution that solves this in big O of n squared time. Now, let's look at the optimal approach, a greedy algorithm. The key insight is this. Instead of trying every possible row arrangement, we handle one position at a time. For each position I, we find the nearest row below it that satisfies the trailing 0 requirement, then bubble it up to position I. Here is the step-by-step breakdown. Step 1. For each row, count the trailing zeros and store the result in a zeros array. This is the same pre-processing step as before. Step 2. For each position I from 0 to n-1, we determine the requirement. The row placed here must have at least n-1-i trailing zeros. Step 3. Starting from row I, scan downward to find the nearest row j that meets the requirement. Step 4. Bubble row j up to position I by repeatedly swapping it with the row above it. Each individual swap adds 1 to our total count. Step 5. If we scan all the way down and find no valid row for position I, it is impossible, return -1. Now, why does the greedy choice work here? Because the requirements are independent for each position. If a row is valid for position I, and also for position I+1, we should take it now. Skipping closer valid rows can only force us to do more swaps later. This approach avoids generating all permutations entirely. Let's look at the code next. Now let's walk through the optimal Python code line by line. The function takes the grid as input. We start by getting n, the size of the grid. Step 1 is the same as before. We scan each row from right to left and count trailing zeros, storing the result in the zeros list. We initialize swaps to 0. This is our running total. Then comes the greedy loop. For each position I from 0 to n-1, we compute need, the minimum trailing zeros required for this position. That's n-1 minus I. We set j equal to I and scan downward. The while loop moves j forward as long as j is within bounds and the row at j doesn't have enough trailing zeros. If j reaches n without finding a valid row, we return -1. It's impossible. Otherwise, we bubble row j up to position I. The while loop swaps j with the row above it one step at a time, incrementing swaps and decrementing j on each iteration. We only swap the zeros values. We don't need to move the actual grid rows, just the trailing zero counts. Finally, after processing all n positions, we return the total swap count. Notice how compact this solution is compared to the brute force. No permutation generation.
No inversion counting.
Just one pass with a scan and a bubble. That's the power of the greedy insight. Let's analyze the complexity of the optimal greedy solution. Starting with time complexity. The preprocessing step, counting trailing zeros for every row, takes big O of n squared. That's n rows, each with n columns to scan. The outer loop runs n times, once for each position. Inside, the scan to find a valid row takes at most n steps. And bubbling the row up also takes at most n steps. So the inner work per iteration is big O of n. Combined, the total time complexity is big O of n squared. Now for space complexity. We only store the zeros array of size n. The variables I, j, and swaps are just integers, constant space. And critically, we never make a copy of the grid or generate any permutations. So space is big O of n. The verdict is excellent. Big O of n squared time and big O of n space. For n equal to 200, that's at most 40,000 operations, completely practical. Compare this to the brute force, big O of n factorial times n squared. The greedy solution is astronomically faster. Next, let's see how the two approaches connect and what the key conceptual shift was. Now, let's connect the two approaches and understand the fundamental shift in thinking. The brute force thinks globally. It asks, what is the best arrangement out of all possible row orderings? To answer that, it generates every permutation, checks each one for validity, counts the swaps needed to reach it, and picks the minimum. This is exhaustive. It never misses the answer, but it is incredibly slow. The optimal approach thinks locally. For each position, it asks just one question: what is the nearest row below me that satisfies my requirement? It doesn't think ahead to the rest of the grid. It just greedily picks the closest valid row and bubbles it up. The key shift is this: we stop treating the grid as one global puzzle to solve all at once. Instead, we recognize that each position has exactly one independent requirement. And for each requirement, the locally greedy choice, take the closest valid row, also happens to be globally optimal.
Why?
Because taking a closer row uses fewer swaps. And since later positions can only benefit from having fewer rows above them moved around, there is never a reason to reach past a closer valid row. This is a classic greedy pattern. Local optimality leads to global optimality. Once you see it, the solution becomes elegant and simple. Next, we'll wrap up with a comparison table. Let's wrap up with a side-by-side comparison of both approaches. Starting with the overall approach. Brute force tries all n factorial row permutations. The greedy solution does a scan and bubble for each position, much simpler. Time complexity. Brute force is big O of n factorial times n squared, completely impractical. The greedy solution is big O of n squared, a massive improvement. Space complexity. Both approaches use big O of n space. For n equal to 200, Brute force cannot finish. The number of permutations is astronomical. The greedy solution needs around 40,000 operations, fast and well within limits. Handling the impossible case. Both correctly return -1. Code length. Brute force needs about 20 lines plus an import. The greedy solution is around 15 lines with no imports. Cleaner and simpler. That wraps up LeetCode 1536, minimum swaps to arrange a binary grid. Thank you so much for watching this tutorial. I hope you found this lesson helpful and easy to understand. If you enjoyed this video, please hit the like button. It really helps the channel grow. Don't forget to subscribe to the channel for more beginner-friendly programming tutorials and helpful tips. Feel free to comment your questions or thoughts below. I love hearing from you, and I try to respond to every comment. And don't forget to hit the bell icon so you get notified whenever I upload new videos. See you in the next lesson.